Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we're going to look at two electrolytic cells that have very special functions and are very unique, and are two big-time uses of electrolytic cells. So the first one we're going to look at is electroplating. Electroplated materials are everywhere around us. Faucets, taps, door handles, sinks, you name it. You can pretty much not walk into a room and not see something that's been electroplated with some type of metal. So electroplating is a massive part of electrolytic cells, and we're going to focus on this first. Now, all the basic rules apply. For electrolytic cells, all the same acronyms, all the same ideas. We're just doing something very specific with the electrolytic cell. So a key point here is when you are electroplating, the object that is being plated must always be attached to the cathode side of the battery. The reason why is cations move towards the cathode, and the metals being plated onto the object are going to be coming from cations that are metals. So we need that metal cation to move towards that electrode and to pick up two electrons and turn from an ion into a solid piece of metal. So what that also means is I need that metal to be plated to be present in the electrolyte solution. So for instance, we are going to do a plating with nickel. So I would want to attach whatever I'm plating to the cathode. So I'm going to plate an old-fashioned key. So the cathode is going to be an old-fashioned key. And in the electrolyte solution, I'm going to put nickel 2+ because I'm going to want it to gain 2 electrons to turn into nickel solid. Now, probably the most common metals that are used in electroplating, copper, nickel, cadmium, chromium, zinc. Zinc, you can dip it or you can electroplate it. But all of those are really, really common. So things like tools, like wrenches and stuff, there'll be multiple layers of electroplating with different materials to increase strength, durability, look, all types of things, okay? So, and generally, if something costs more than and it's metal, it's because it's been plated multiple times with multiple things. That's what increases the price of it, okay? So I'm going to go down here. We're going to look. Here's my giant electrolytic cell. I'm going to draw an old-fashioned key. I remember when I moved to London, England, I had about a 4-inch key that looked something like this, and I thought it was a joke when it was given to me. It was a massive key, barely fit in your pocket. So, first thing we got to do, draw an old-fashioned key. Mine doesn't look that great, but that's okay. So this is going to be the cathode. So this key was probably originally made out of steel or iron, and then it's going to get plated because iron corrodes so easily. If you plate it, it won't corrode, and it'll also make it look a lot nicer. Okay. The next thing I have to do is clarify what my anode is. So I'm going to make this the anode, and I'm just going to call it a piece of platinum. It could be carbon. It could even be nickel. So sometimes we actually make the anodes out of the substance that is to be plated onto the object. And sometimes we just use an inert electrode. So this technically could be platinum. It actually could even be a bag filled with pieces of nickel metal. Either of them would work. So then I'm going to put in nickel 2 ions in solution, and I'm just going to use nitrate ions because nitrate is 100% soluble with everything. It's probably what it's going to be dissolved in water anyways. So this is going to be an aqueous solution, so I fill this up. So I got a nickel nitrate solution in here. I can start doing some of my general cell things that we always do. So we'll do all the flows. So electron flow is always through the wire from the anode towards the cathode, like this. So there's my electron flow. Now the most important part here is going to be the nickel flow. So the nickel is going to be moving towards the cathode because cations move towards the cathode. And then the anions move towards the anode, so I'm going to have the nitrate moving this direction. Now, before we start doing our reactions, we should do a species list. So I'm just going to do a species list underneath here. We have a nickel 2 plus ions, aqueous. We have nitrate ions, aqueous. And of course, we have water. The cathode would never lose mass, so I'm not including whatever material it's made out of. And the anode is inert, so I'm not including the platinum in my list. So here's my species list. The strongest oxidizing agent would be my nickel 2 plus ion. This is neither because it's not acidified and it's inert. This is either an oxidizing agent or a reducing agent. However, because it's the only reducing agent, it must be the strongest reducing agent. So in electrolytic cells, it is not uncommon to have water reacting at either the anode or the cathode. I would say, half the questions we do, water is either going to be a strong oxidizing agent or a reducing agent. So if that's the case, I look at my nickel, and I should clarify, the water is above the nickel 2 plus on the reduction half reaction table. So this is a non-spontaneous reaction. That's why this is an electrolytic cell, because we're forcing something to happen which doesn't want to happen. And in order to do that, of course, we need to have a power supply. All right, let's write out these half reactions. So I have nickel 2 plus aqueous is gaining 2 electrons on the surface of the key. So when that nickel 2 plus hits the key, it's going to pick up those 2 electrons, and that's going to turn into nickel solid. So the evidence here is this key will gain mass and will be coated with nickel solid. Okay. The nickel 2 does have a solution color. I believe it's a little bit blue-green. So as this runs, the solution should become less blue-green because the nickel ions are being consumed. On the anode side, we have to have water as a reducing agent. So I'm going to flip it, the reduction half reaction to an oxidation half reaction. So this is 2H2O liquid is going to become O2 gas plus 4H plus aqueous plus 4 electrons. So in order for this to be balanced properly, I would have to multiply the nickel half reaction by 2. So this would be 2, 4, 2. We can do a net reaction here as well. So if I put those two together, my net reaction would be 2 waters plus 2 nickel 2 plus aqueous, turning into O2 gas plus 4H plus aqueous plus 2 nickel solid. We should check that the balancing is correct using the total charge. So 2 times no charge is no charge. 2 times 2 plus is 4 plus. 1 times no charge is no charge. 4 times 1 plus is 4 plus. 2 times no charge is no charge. So we've got a grand total of 4 plus, and we've got a grand total of 4 plus. It's balanced properly. Forgot to do evidence around the anode. So when I look here, I have oxygen gas being produced. So I'm going to see some bubbles. So there's going to be bubbles on the electrode, bubbling out of solution. The solution is also becoming acidified. This is acidic. So the pH would decrease. So there's your key points for how to do an electrolytic cell that is going to electroplate any item. Whatever item you want to plate must be on the cathode side. It must be attached to the cathode side of the battery. Whatever metal you want to plate on that object must be in solution. You can use an inert electrode for the anode, or I could have, if I wanted to, I could have used nickel solid here as well. I could have used nickel solid, which would have actually lost mass and would have replaced the nickel 2+ ion, but I just chose not to. No big deal either way. And all the basic things stay the same. ACE, anode to cathode, move electrons. C to C, cations towards cathode. A to A, anions move towards anode. The two half reactions, net reactions, etc. The next type of specialty electrolytic cell we're going to look at is the chloral-alkali process, or it's often called the chlorine anomaly, because it is an anomaly. It goes against kind of everything that we've learned in terms of what species are going to react in solution. The gist of it is this. When you have a chloride ion in solution in an electrolytic cell that's aqueous, this is going to be the strongest reducing agent, even though technically it is not the strongest reducing agent. So there's kind of three cells that generally have a chloride ion in it that are fairly popular for this process. Aluminum chloride aqueous cells, sodium chloride aqueous cells, and nickel 2 chloride aqueous cells. This is probably the most common, a saltwater cell. And so I'm going to use a saltwater electrolytic cell in order to explain this. So if I was to do a species list for a saltwater electrolytic cell, I would have sodium ions aqueous, I would have chloride ions aqueous, and I'd have water liquid. Now, what I've done down here is I've just taken a little snippet of the three relevant reactions that would be part of this species list, okay? So I would have water as a oxidizing agent here. Sodium ion is down here, but it isn't a strong enough oxidizing agent to participate. And then I have water here, which is technically the strongest oxidizing reducing agent. And I have chloride here. So normally what we do is we take our strongest oxidizing agent going up this way, which would be water. This is my SOA. And I take my strongest reducing agent coming down, and water would be my strongest reducing agent. And I would have a water-water reaction, which is totally fine. This is something we also do, is in a Hoffman's apparatus, you can just have, say, sodium nitrate in it. And then you get this water reaction happening on one side, on the cathode side, and you have this reaction happening at the anode side, and it's something that is actually done, okay? But that's not what's going to happen here. So even though water is the strongest reducing agent here, it's actually chloride that reacts, and we get this reaction here instead of the water-water reaction. Now, you do not need to explain why. I'm not even going to go into it. You just have to memorize that this is an anomaly that happens. And when you have chloride ion in an electrolytic cell, it ends up being the strongest reducing agent, not water. The chloride becomes the strongest reducing agent. This is the anomaly. You just have to memorize it. Now, there is one minor stipulation. In order for this reaction to occur, the power source must supply a voltage of 2.9 volts or higher. That would be the minimum voltage in order to get this reaction to happen. Now, most electrolytic cells are going to be definitely over 2.19 volts. I mean, we use 9-volt batteries, those little rectangular batteries and stuff, and we can do this with a 9-volt battery. So there's very few electrolytic cells that wouldn't be over 2.19 anyways. So to be clear, all you really need to know for this type of cell is when you have a species list in an electrolytic cell and chloride ion aqueous is present in that species list, this is going to be the strongest reducing agent for sure. This needs to be memorized. That's it. The strongest oxidizing agent could be water. In the aluminum chloride and in the nickel chloride cells, water is the strongest oxidizing agent. In the nickel 2 chloride cell, the nickel is actually the strongest oxidizing agent, and it'll plate at the cathode. Okay, so you do not need to explain why this happens. You just need to memorize this. So I'm going down here, and I'm going to write this out. We're going to call one side the anode. I'll call this side the anode. I'm going to make it inert, make it platinum. I'm going to call this the cathode. Again, I'm just going to make it inert. I don't want it to participate in the reaction. I'll make it out of platinum. So when you have this scenario, again, sodium ion, chloride ion, and water liquid in an electrolytic cell, your brain has to tell you, hey, I've got chloride in this electrolytic cell. This is the SRA. I just have to memorize that. And so what I'm going to do then is write the half reaction that occurs at the anode here now, which is 2Cl minus aqueous becoming Cl2 gas plus 2 electrons. I'm just going to focus on this side before I go to the cathode side because this is really the important side. What's going to happen is you're going to have bubbles of chlorine coming off of this. So those are Cl2 bubbles. Now, chlorine gas is used in all types of things, but especially in like bleach, okay? And it's used a lot in organic chemistry as well. This is a highly sought after chemical compound. So if this was an actual cell that produced this at an industrial level, there would actually be essentially a vacuum tube above it, and it would suck the gas off the top of the electrode out, and it would be collected. Okay. Now on the cathode side, I have water as an oxidizing agent. So that half reaction would look like this. 2H2O liquid plus 2 electrons turning into H2 gas plus 2OH minus aqueous. And so we would also have bubbles on here. We would have hydrogen bubbles, which are also extremely useful. Hydrogen gas can be used as a fuel to be burned. It can also be used as a chemical compound using organic synthesis. It could be used in saturation reactions. There's lots of use for hydrogen gas. And then you're also producing, so I'm going to see bubbles, and then you're also producing hydroxide, which is a very useful substance. And actually, if this is sodium chloride, you're really making a sodium hydroxide solution, which is basic, which can be used as sodium hydroxide for chemistry, but it's also called caustic soda. That's a common name for sodium hydroxide. You might not have ever heard that before. In Alberta, a lot of caustic soda is used in the pulp and paper industry. So Hinton has a massive pulp and paper factory, I guess. I don't know if I would call it a factory, but it has a huge pulp and paper industry there. Now, we didn't put in our ions in solution. So let's put them in. We'd have sodium ions and chloride ions. Cations go towards the cathode. Anions go towards the anode. And of course, electrons go through the wire from anode to cathode. Now, there's 2 moles of electrons on each of these, so those would cancel out nicely if I want to do my net reaction. And so that would be 2Cl minus aqueous plus 2H2O liquid, turning into Cl2 gas, a very useful chemical compound, H2 gas, a very useful chemical compound, and 2 hydroxide ions, strong base, also a very useful chemical compound. So we'll double check our balancing. 2 times -1 is -2. 2 times nothing is nothing. 1 times nothing is nothing. 1 times nothing is nothing. 2 times -1 is -2. This is a 2 negative total and a 2 negative total. So we've looked at 2 very specific electrolytic cells in today's lesson. We've looked at the electroplating of metals to something attached to the cathode side of an electrolytic cell. Extremely useful industrially. We see it around us all the time, okay, in our everyday life, electroplated objects. And then the chloral-alkali process, or chlorine anomaly, which is just a weird thing that you have to remember, that when you have a chloride ion in an aqueous cell, it is going to be the strongest reducing agent, even though water should be. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.